Hey guys, welcome back. So in this video, we will continue our discussion on the JVM fundamentals. And in this video, we will talk about JVM opcodes and class file structure. So these are the foundations of how Java programs are actually understood by the JVM. So let's get started. So let's start with the opcodes. What are opcodes? In JVM bytecode, an opcode is an instruction that tells the JVM what action to perform. So an opcode represents a specific operation, a specific task. It could be like loading a value to the operand stack, or adding two numbers, or creating a new object, or invoking a method. So an opcode is like a command that the JVM understands. In the .class file, an opcode is typically 1 byte long, and it may require some operands. So the bytecode instruction is basically, it starts with opcode. So we have the opcode and it may be followed by the operands. So opcode tells what action to perform and operands tell on what values. So this is an example of an opcode which says iload_0. Now this opcode tells JVM to load an integer variable from the local variable table. So this is the slot. So it says that from the local variable table, you have to load the value which is at slot 0 onto the operand stack. So you can see that the concepts are building together. In the last video, we covered the operand stack and the local variable table. Moving on, and here we can see the description of iload opcode from the VM specification. So you can see the syntax. It starts with iload, then we have the n basically tells the slot in the local variable table. So if the bytecode has iload 0, it means pick the integer value from the local variable table which is at slot 0. iload 1 means integer value which is at slot 1 in the local variable table. However, if we check the .class file directly, we won't see these values because we know in the .class file these are the streams of bytes. So we will see values like 1a which is the hex value, or 26 which is the decimal value. Most probably we will see the hex values which is 1a, 1b, 1c, something like this, or the corresponding hex value of this decimal value which represents the instruction iload in this case. But when we check the bytecode, let's say using IntelliJ or using a deassembler, then we would see in the file that the instruction is iload, not the hex value. Now here we see some of the common opcodes that you will see in the bytecode, although it will change depending on the code we write, but these are some of the common opcodes. And you can see the category, for example, load and store. So the common opcodes that you will see is iload, istore, basically load the value from the local variable table onto the operand stack. Then istore means store that value back to the local variable table. Alright, aload is to basically load the reference, not the primitive value. And similarly, astore is the counterpart. Then we have another category like arithmetic, which is basically to perform basic math operations like adding the values, subtracting the values, multiplication, division, so on and so forth. To handle the objects, we have different opcodes like new to create a new object, check cast to basically perform the casting operation to check whether two types are compatible with each other. Then we have another category of method invocation. So in this category, we have different invoke methods to call different methods. All right. So for example, invoke static will be used in the bytecode where we are calling a static method. All right. On the last slide, what we covered was a subset of common opcodes, but you can see or you can find the full list in the JVM specification. So if you just follow this link, this is for SE7, just change the version. And here in this page, you can see all the opcodes listed here and you can find the details. So for example, if I go to AA load, so here I can see the description that this loads reference from array, and this is the format that you will see in the bytecode. This is the code, basically the hex code that we will see in the .class file, and the operand stack, what it expects, and the description as well. And similarly, you can find the details of other opcodes as well. So in a nutshell, opcodes are simple instructions which tell JVM what to do. So far, we have covered the fundamentals. We will learn these things in detail when we cover the actual bytecode in upcoming videos. Alright, next we will cover the class file format or the structure of the class file. So we know when we compile the Java program, it generates a .class file, and this .class file has a definite structure. It's not random. In this .class file, as you can see on the screen, there are different fields in a particular order, and we can find this information on the JVM specification. In fact, this screenshot is directly taken from the JVM specification. So what happens in the generated .class file, there is one thing which starts the whole structure, and that is the magic number. And you can see that is the first thing on the structure. So that is the magic number. Magic number, you can say, is like a signature that ensures that the file is recognized by the JVM as a valid class file. After the magic number, we have minor and major versions. Now these versions represent Java releases. So for example, code for Java 8 is 52, and for JDK 17 it could be 61. And when we define a particular minor version and major version, this is done automatically. We don't have to specify it, but it defines a range. Now this range defines that your code is guaranteed to be compatible with a Java version if it lies between the minor version and the major version. Then comes the constant pool and the size of the constant pool. And this is one of the most important parts, because the constant pool is a table-like structure which represents various constants which are used in the class file. It could be string constants, name of the classes or interfaces, name of the fields, or even method names. So it stores the symbolic references to all these constants. Then comes the access flag. Access flag tells whether a class is public, abstract, final, interface, so on and so forth. It basically tells the access level of that class. Then we have the fields related to this class and superclass. These fields simply describe the class name and its superclass name. And similarly, we have the interfaces count and a list of interfaces that this class implements. After the interfaces, we have fields and methods, and they follow the same pattern. So the class file has a record of all the fields in the class file, similarly all the methods. And for each field or method, it stores the metadata related to the access flag, which is again the accessibility of that field or method. It's indexed in the constant pool so that the name can be referenced, and some attributes which belong to the metadata. And in the end, we have attributes which basically represent the various metadata blocks present in the .class file. Alright, so that is the overall class file structure, and it might seem that we are just scratching the surface, and of course we are. In this video, we explored the internal layout of class files and the opcodes, but in upcoming videos, now that we have covered the basic knowledge, we will go deeper. We will inspect the bytecode, we will do some hands-on, we will do some dry runs. We will see how everything that we have learned so far connects together in order to understand the bytecode that is generated when we compile the .java file. So that's all for this video. I will see you in the next video, in which we will dive deep into the bytecode. Thanks for watching.